you're gonna start by initializing the PageRank of every node to a constant, right? So you're gonna take 1 over n, where n is the number of nodes that you have in the graph. And that's going to be your initial PageRank for the node. So initially, every node in the graph gets exactly the same PageRank, and the PageRank adds up to 1. In these slides, I'm actually going to I'm going to use 100% rather than 1. It's really the same thing, right? They're off by a factor, but I'm going to run with percentages. So initially, you take your 100% PageRank and you split it up over all the nodes equally, right? So in this case, I have 11 nodes in this graph, so every node would get a PageRank of 9.1%, right? So it's splitting equally. By the way, this is the PageRank that every node would have if I had no edges in the graph, right? Because if I have no edges in the graph, then I'm always going to be hopping around randomly from node to node, and the chance that I end up at node E is exactly 1 out of 11, because I have equal chance of getting to E at any point in time, if you have no edges. Okay, great, so that's what you initialize it to, and then you compute the PageRank. So how do you compute the PageRank? You use this equation to compute the PageRank for node X. So let's walk through it and see how this equation actually comes up, right? And I'm briefly going to use the board for this, right? So I want to compute the PageRank of node X, right? Now, think about it. What is PageRank at node X? It is the probability that in the current moment in time, I'm going to be at node X, right? So to be at node X, I have to get there in some way. And how can I get to node X? I can get there in 2 ways, right? On the previous step, I flipped a coin, and that coin either came up heads or it came up tails. So that's what the lambdas correspond to. With probability 1 minus lambda, the coin comes up tails. Right? And with probability lambda, the coin comes up heads. Okay? So when the coin comes up tails, what happens? I take a random hop, right? So I was somewhere in the graph, and I take a random hop. Now, during that hop, what is the chance that I land at X?
1 divided by n.
It's 1 divided by n, right? Because you take a random hop, and you're equally likely to land on any node in the graph. So it's 1 divided by n. That's the probability of ending up at X through a random hop. Okay? Now that's if the coin came up tails. If the coin came up heads, something different happens, right? When the coin comes up heads, I don't take a random hop. So the only way I can end up at node X is if I were at some other node which points to X, right? So let's say I was at a node Y, and the node Y points to X, right? Now, if I actually was at that node, and I know the coin came up heads, do I always end up at X? No, I don't, right? Because I've got a node Y, I've got a node X, and I know there's an arc going from Y to X, but there could be other arcs going out of Y, right? So what is the chance that I end up at X? 1 over the number of outgoing links, right? So it's 1 divided by the out degree of Y. Now, that's if I was at node Y on the previous step, okay? Now, what is the probability that I was at node Y on the previous step? It's the PageRank of Y, right? That's the definition of PageRank. The definition is PageRank is the chance, the probability that you were on that node at a random moment in time. So the probability that I was at Y on the previous step is just the PageRank of Y, right? So take that, multiply it by the PageRank of Y, right? So that gives me the probability that I was at Y, and Y has a link to me And when I was at y, I randomly picked exactly the link that goes to x. That's one out. That's the out degree. Okay, great. Now the good thing is y is not the only node that points to me. Maybe there is another y, like maybe this was 1 by 1 and this is 1 by 2, and y2 also points to me. So I want to aggregate these quantities over all nodes y that point to me. So the way you do it is you sum it up over all the nodes y that point to x, probability that I was at that node on the previous step times the probability that the next hop is going to be 2x, right? And all of that happens only if the coin comes up heads. And if the coin comes up tails, that's the probability. And then, of course, I add them together because in both cases I have a chance of ending up at node x. Does this make sense? So that is that equation right there. Just a little bit spread out for you. So what's happening in that? Another way to think about that is how the PageRank is pooled by every node from its surrounding nodes. You can also think of pushing the PageRank around, right? So each node y takes its PageRank and divides it evenly among the nodes that it points to. So it sort of shares the wealth, shares the PageRank with the nodes that it points to, and it shares it equally based on the outlinks that you have. Okay, great. So that's the way to do it. Now, the tricky thing is, as you're doing it, you want to make sure that at every point in time, your PageRank adds up to 100%. So this is an update for one node, and then you want to do the same exact update for every node in the graph, right? For A, B, C, D, and so on. And what you want to make sure is you want to make sure that at the end of this update, the PageRanks add up to 1. And the way to make sure that this happens, if you're doing it in a regular way, so if you're just writing a piece of code, not a MapReduce program, is to have 2 arrays, right? So that is probably the most common mistake. People try to do it in place, right? You actually need 2 arrays for maintaining the PageRank. The PageRank at the previous step and the PageRank at the current step. If you try to do it in place, you'll quickly end up with PageRanks that are either a lot bigger than 100% or a lot smaller than 100%. Okay, so let's run through an example for the computation, right? So we're going to compute a PageRank for the node B, that node right there. Okay, we're just taking the equation and saying, so let's say that for no good reason whatsoever, lambda is 0.82 and 1 minus lambda is 0.18. Right. So what is going to be the PageRank of B at the first iteration? So at the first, actually, this is not just the first iteration. This is any iteration, but the final number is specific for the first iteration. Right. So this is the fraction of PageRank that comes from the random hop. It's 1 minus lambda times 1 over n, like that part. And then you have plus lambda times what? Times the contributions that node B is going to receive from all of its neighbors. And what are these contributions? So at the moment, I've just, at iteration 1, all of the nodes are initialized to 9.1% initial PageRank, right? That's just 1 over n, that number right there. Now, what fraction of their PageRank do they contribute to B? Well, that's just based on how many outlinks they have, right? So node C, for example, has only 1 outgoing link, so it's going to take all of its PageRank, 9.1, and give it all to B, right? So you get the entirety of PageRank C. Node E has 3 outgoing links to B, to D, and to F, so it takes its current PageRank, which is 9, divides it by 3, and gives a third to B. So B is going to get 3 from node E, 1/3 of the PageRank, and so on and so forth, right? So simple and easy. Okay, and that is what you do for node B in the graph. Now then you repeat it and do the same update for every other node in the graph. So you compute node A, you compute node C, and here's an example for node C. The PageRank for node C is, here's the random component, the random hop, probability of a tail times the probability of ending up on the random hop times lambda 0.82 times the PageRank of B. Now, I want to drill this once again. because this is a very common mistake, that this is the PageRank of B, and I'm not taking the new PageRank of B, which is going to be 31. I'm taking the old PageRank of B, which is 9, right? You have the old array of PageRanks and the new array of PageRanks, and don't mix them up. Okay, and then on the second iteration of the PageRank, of course, you're going to be doing the same update for node C, only now you're going to have a new PageRank of B, and the new PageRank of B at the second iteration is 31. So 82% of 31 is going to be, plus that is going to end up giving you a 26. But that's at the second iteration. At the first iteration, you still get 9.1. Right. Okay. So that's PageRank. That's how that's how you implement the algorithm. That's the intuition behind the update rule. And this is how you want to implement it. Don't try to, if you're implementing single core, don't try to push PageRank around. Try to pull it from the neighboring nodes and have 2 arrays. That's going to give you a very efficient implementation, as long as you have a nice way to represent the incoming and outgoing links, right? So don't use a full matrix. Use sparse lists for representing in links and out links, and then everything is going to run beautifully for you. By the way, I guess if what I just said didn't make sense, use the same representation that you used for courseworks 1 and 2. Right? The way you represent a sparse graph is exactly the same as the way you represent a collection of documents and words. It's exactly the same problem. It's beautiful. 2 completely different domains, but you use exactly the same data structures, and they give you the optimal runtime.